In this lesson, we want to talk about sequences. All right, so in this chapter, we're going to do a deep dive into sequences and series. And we're just going to start out with this lesson, which is just going to be an introductory lesson to sequences. We're just going to learn about the notation and kind of how to plug in for things. So I want to start out with just a simple example. We have a sub n is equal to 2n. So before I go any further, let me just tell you that a sequence is nothing more than just a function that computes an ordered list. And the domain of this function, what's allowed to be plugged in here for n, would be the set of natural numbers, right? Or the set of positive integers. So remember those, if I said n was the set of natural numbers, this would be starting with 1 and going out to positive infinity, right? You're just increasing by 1 each time, okay? So that would be the set of natural numbers, or again, positive integers. So what we could say here is that a sub n is equal to 2n. I could relate this to something like f of x equals 2x, where I specifically restrict the domain to say that x is a natural number. Okay, I'm just going to put an n there. Okay, so a natural number. So we would know that if we wanted to plug in natural numbers for x to kind of generate some ordered pairs, or if you wanted to see what the function's value was, then I could say, okay, the first one, or the first natural number is 1. So f of 1 would be what? We'll just plug in a 1 for x, and you would get 2 times 1, which is 2. Then if I wanted f of 2, again, you'd plug in. So 2 times 2 equals 4. So on and so forth. F of 3 would be 6. F of 4 would be 8. Again, so on and so forth. Now we do the same thing with a sequence, but it looks a little bit different because we're using this a sub n notation. Okay, so the way we would say this is we would say a sub 1. Okay, so a sub 1 is me plugging in a 1 for n. It's the same thing as f of 1 here. Okay, so this is a sub 1. That's how we write this. So a sub 1 is equal to 2 times 1. Okay, again, here I plugged in a 1, here I plugged in a 1. I'm just plugging in for n, whatever's right there. It's just like if I said f of 1 is equal to 2 times 1. It's the same thing, it's just different notation. Okay, so a common task here is just to go through and write the first 5 what we call terms of the sequence. So this result here is a term, okay? So if I said a sub 2, that would be 2 times, again, just plugging in a 2 for n. So this is 4. If I said, and let me just kind of erase this. If I said a sub 3, what is that? That's 2 times 3, which is 6. And we're just going to be increasing by 2 each time, right? So we'll say that a sub 4 is going to be 8, and a sub 5 is going to be 10, okay? So another common task, let me just kind of copy this real quick, will be to plot these guys on the coordinate plane. And let me just kind of clean this up. So let's say this is 2, 4, 6, 8, and 10, okay? So you can kind of think about these as ordered pairs, okay? Just like if you had x and f of x, or x and y. But now we have n, okay? And we have a sub n, okay? So this is just like if you had x and y, or x and f of x. So if a sub 1 equals 2, again, 2 is called the term, okay? But really we think about this as, again, if I had f of 1 equals 2, 2 is your y value, okay? So 1 is what I plugged in, okay? 1 is what I plugged in, that's your x as we think of it. 2 is what I got out, okay? That's my y as I would think about it. So now it's going to be the n and the a sub n. So I want a 1 going along my n axis, okay? And I want a 2 going along my a sub n axis. So it's going to be right there, okay? So this is going to be this 1, 2, okay? Then you have 2, 4. So again, you're just grabbing this and this. So 2 and then 4. And we already know how to plot ordered pairs, so we don't have to spend a lot of time on this. But you have 3 and then 6. So we'll have that there. And then we have 4 and 8. So 4 and 8. See if I got that right. Okay. And then 5 and 10. So 5 and then 10. Now, what's interesting here is that you're not going to connect these points, okay? Because if I had something like, let's say f of x equals 2x, well, in this case, your domain is the set of real numbers. So we could connect those points with a line, and all the points on the line would satisfy your function, okay? But in this particular case, it doesn't work that way because we've restricted the domain for n to be the positive integers, or the natural numbers. So you have 1, 2, right? 1 is n and 2 for a sub n. And then the next guy that you can plug in is 2. And the value for a sub n, or the term there, is going to be 4. Okay, so you're going to get these jumps here. You're not going to connect this with a line. All right, let's just try another example. Again, when you first get to this, you're just going to be plugging in and getting used to the notation. So we have a sub n equals 4 minus 10n. If I wanted to find the first 5 terms of the sequence, all I'm going to do is I'm going to start out with 1, okay? Because that's the smallest natural number. That's always what I'm going to start with. So I'm going to say, what is a sub 1? And all I do is I plug in a 1 for n. So 4 minus 10 times 1, okay? If I want a sub 2, I'm going to have 4 minus 10 times 2, okay? If I want a sub 3, I'm going to have 4 minus 10 times 3. If I want a sub 4, I'm going to have 4 minus 10 times 4. If I want a sub 5, I want 4 minus 10 times 5, okay? And you're going to see a pattern here because 4 is always the same. Really, once I get my first number, I'm going to decrease by 10 each time, okay? And that's because this 10 is multiplying this guy here. We'll talk about how to go from the results or the terms, okay, back to the formula later on in the chapter. For right now, let's just kind of crank these out. 4 minus 10 would be negative 6. And then as we get here, 10 times 2 is 20. So 4 minus 20 is negative 16. And again, you're just decreasing by 10 each time. So this would be negative 26, negative 36, and then negative 46. Okay, let's do one more real quick. So we have a sub n equals 1/3 raised to the power of n, and then times n minus 1. Okay, so this one's a little bit more tricky. But again, all I'm doing is plugging in there and there, okay? So I have a sub 1, always start with 1, okay? Then you have 1, let me kind of write this a different way. So 1/3 raised to the power of 1 times, you're going to have 1 minus 1. And we know that 1 minus 1 is 0, and anything times 0 is 0. So we can just say this is 0. Okay, so that's the first guy. Then a sub 2 would be what? Well, I'm plugging in a 2 there, so you'd have 1/3 squared times 2 minus 1 is 1. So 1/3 squared would be 1/9. 1/9 times 1 is 1/9. Okay, so we've got that. Then a sub 3, let me just kind of write this over here. So a sub 3 is what? You would have 1/3 cubed, so you know that's 1 over 27. And this is times 3 minus 1 is 2. So this will just be 2 over 27. So 2 over 27. And then we'll have a sub 4, okay? So I know 1/3 raised to the 4th power, all I'm going to have is 1 over 81. So 1 over 81, then times 4 minus 1 is 3. So now I can cancel here. I can cancel here because this and this have a common factor of 3. So this will be 1 and this will be 27. So this would be 1 over 27. Okay, so 1 over 27. And then for the last guy, a sub 5, what do we get? 1/3 raised to the 5th power. Well, 3 to the 5th power is 243. So 1 over 243. And then times, if you did 5 minus 1, that's 4. So this is going to just be 4 over 243. Okay, let's talk a little bit about a recursive definition. This is where each term after the first term, or it could be the first few terms, is going to be defined as an expression involving the previous term or terms, okay? So here what we see is a sub n plus 1 equals a sub n plus 30, specifically if n is greater than 1. So we're still working with the set of natural numbers, but specifically this definition here, okay, that's given to us is only going to work if n is greater than 1. They've given us the fact that a sub 1 is equal to negative 21. So we have the first term of the sequence. It's negative 21. If we wanted a sub 2 and a sub 3 and a sub 4 and a sub 5, what we're going to find is that we really just take the previous term, okay, and add 30. That's all we need to do. But how could you show this? So let's start out with this. So if I wanted a sub 2, I could break this up and show this as a sub 1 plus 1 like this, and say, okay, this is a sub 1 plus 30. Okay, so now it's clear that a sub 1 is negative 21, so I'm just plugging that in there. And this is going to be 9, right? And I'm going to rewrite this as 2. I can break this up into a sub 2 plus 1, okay? And so what I would say here is that this is equal to my a sub 2, which is 9, just grab that from there, plus 30, okay, which is going to be 39. Okay, and again, we're going to just keep doing this. Let me rewrite this as a sub 3. I could write a sub 4 as a sub 3 plus 1, right, if I wanted to. So again, I would just take a sub 3, which is 39, and add 30. Okay, so this is 69, right, so on and so forth. Here, I would just take 69 and add 30, and I would get 99, right? If I wanted the next one, I would start with 99 and add 30, so on and so forth. In this lesson, we want to talk about series and also the summation notation. All right, so in our last lesson, we talked about the fact that a sequence was a function that computes an ordered list of numbers. So I have a basic example here. We have something like a sub n is equal to 2 times n. So remember, this is the new notation that I introduced to you. You could just as easily write this as f of n is equal to 2 times n like this. These two are the same, okay? It's the same. This is the typical notation you're going to see with a sequence. Now, when we work with a sequence, remember, this n here is telling me or reminding me that my domain, or what I can plug in for n, is the set of natural numbers. So this is the set of numbers that starts with 1, so that's the smallest, and increases by increments of 1 out to positive infinity. So you could say the natural numbers or the positive integers, whatever you want to do there. But if I ask you for, let's say, the first 4 terms, you've got to remember that the smallest natural number is 1, so that's what we start with. So we say a sub 1 is equal to, all I'm going to do is plug in for n. I put a 1 there, okay, right here. So I'm going to put a 1 right there. So this is 2 times 1. Just relate this to what we already know. If I had f of 1, what would I do? I would plug in a 1 for n. So this would be 2 times 1 like this, which is 2. Same thing, different notation. Okay, let me erase this. Now, I said the first 4 terms. So let's go a sub 2. This is 2 times, again, plugging in a 2 now. So this is 4. Then I want a sub 3. This is 2 times, plug in a 3 now. This is 6. And then lastly, I'm going to want a sub 4. So this is 2 times 4, and this would be 8. Now, this could go on forever. I just asked for the first 4 terms, right? So I got 2, 4, 6, and 8. But you could do this as long as you wanted to, right? There's nothing stopping you. There's an infinite number of natural numbers. So after 4, I could go to 5, then 6, then 7, so on and so forth, out to positive infinity. Now, with a series, this occurs when we find the sum of the terms of a sequence, okay? Now, in this particular case, I've just given you the first 4 terms, okay? So I'm going to get a series that's going to be based on these first 4 terms. So what I'm going to do is I'm going to say S for series, and then sub 4, because I just have the first 4 terms. So this is going to be equal to, and I'm just going to grab these guys, so it's going to be 2, okay? That's my first term. My second term is 4. My third one is 6. And my fourth one, where I'm stopping, is going to be 8. And then I just find the sum. So 2 plus 4 is 6. 6 plus 6 is 12. 12 plus 8 is 20. Okay, so that's an introduction to series. Now, when we work with series, we have this special notation that we use, and this is known as the summation notation or the sigma notation. This is something you have to get used to because when you get to calculus, you'll see it a lot. You'll also see it in statistics class a lot. So something you definitely have to get used to using. It's very, very easy to use, but you do have to get used to it. So the first thing you'll notice is this gigantic E-looking letter. And basically, this guy is the Greek capital letter sigma. Okay, that's why we said sigma notation. And basically on the bottom here, you have this I equals 1. So I'm just going to tell you the easy way to remember this is your starting value and this is your ending value, okay? The I here, this is not the imaginary unit I. It's officially known as the index of summation. I always think about it as just a counter, okay? A way to keep track of where you are, okay? Because this is where you're going to start and you're going to increment by 1, okay? So that's how I remember it. I just think of it as a counter. So this is your index of summation officially. The 1 is your starting value, or officially in your book, you're going to see it's the lower limit of summation, okay, the lower limit of summation. The n is your ending value. That's where you're stopping, or you could say the upper limit of summation. If we go back up here, we started with 1 and we ended with 4. So if I come back down here, I would have a 1 here and a 4 here, okay? And then I would just have my rule here, which is 2 times I. In this particular case, we just have a sub I. Okay, so all I would do here is I would plug in a 1 where there's an I. I'm just plugging things in just like I did before. So I would have a sub 1. Then I would increase by 1. Okay, I'm just using the natural numbers. So I'd increase by 1. I'd have a sub 2. Then I'd have a sub 3. Then I'd have a sub 4. And I would stop at a sub 4 because my a sub n in this case would be a sub 4. Okay, because n is 4. But if it was 10, I would go out to a sub 10, right? So on and so forth. So this is your starting value. This is your ending value. That's what you need to know. So if we look at this problem once more, what this is telling me to do, again, just to follow the rule, I would start by plugging in a 1 for I. Okay, so I would say, what is 2 times 1? Then plus, I would increment by 1. So I would say, what is 2 times 2? Then plus, again, I'm incrementing by 1. So what is 2 times 3? Then plus, what is 2 times 4? And that's where I stop because this is my ending value. This is where I start. This is where I end. I'm just plugging in for I. Again, all it is just fancy notation. It's the same thing that we did up here. Okay, this is very easy to read, but when you get to this notation at first, it does seem a bit confusing. So we already know this is 20. So let me just kind of reduce this and just say this is 20. All right, so let's jump in and look at an example. And what we're going to do after this is look at some rules, and I'll show you how to get through this more quickly. So here we have the summation from I equals 1 to 4, okay, we have this 2 times I minus 9, okay? So all I'm going to do here is I'm just going to plug in a 1 to start. So I would have 2 times 1 minus 9, okay? So what is that? 2 times 1 is 2. 2 minus 9 is negative 7. So that's my first value. And then I increment by 1. I started with 1. Now I'm going to 2. So I'm going to have, and let me just do this down here. So 2 times, now it would be 2 minus 9. And what is this? 2 times 2 is 4. 4 minus 9 is negative 5. So I'll put a negative 5 here. Let's just put minus 5. A little bit easier. And then let me erase this. And now we're going to go to 3. 2 times 3 is 6. 6 minus 9 is going to be negative 3. So let's put minus 3. And then let's go to 4. 2 times 4 is 8. 8 minus 9 is negative 1. So let's put minus 1 there. Okay. So now you just go through and add things. Okay. You can think about this as negative 7 plus negative 5 plus negative 3 plus negative 1. So if I did negative 7 minus 5, that's negative 12. Then minus 3 is negative 15. Then minus 1 is going to be negative 16. So that's your answer. Okay. That's all there is to it. Again, you're just plugging things in. Okay. I start with 1. So that's why I start here. And then I increase in increments of 1. Just think about the natural numbers. They increase in increments of 1 until I get to this value here. So I had 2 times 1 minus 9. Then I had 2 times 2 minus 9. Then I had 2 times 3 minus 9. Then I had 2 times 4 minus 9. And you just sum those results, and that's how you get your answer. Let's look at some rules that we're going to need to kind of make this a lot quicker. Some of these, until you practice with them, you're not going to make a whole lot of sense of them. You might say, why do you need them? But then you're going to get hit with problems where they're absolutely necessary to get through them in a reasonable amount of time. So this first one looks a bit odd. So let me just kind of explain this off to the side. So let's say, and I'm not very good at drawing, but let me make this letter here. Let's say this was 5, and let's say this is 1, and let's just say this was the number 6. What does this mean? Because I don't have anywhere to plug in things. Okay, so people get confused by that. What you see the rule is here is that you would just take this here and multiply by this here. So this tells me I would just do 6 times 5, which is 30. But where does that come from? Well, basically, even though you don't have an I involved here, you've got to go through and do this 5 times. So what you would say is that the first one would be 6, and then you would increment and say, okay, now I'm on the second iteration of this. So I would do another 6, then another 6, then another 6, then another 6. So here, I is 1. Here, I is 2. Here, I is 3. Here, I is 4. And here, I, and I'm messing that up, so let me make that better. So I is 5, okay? So it's going to give me 5 iterations of having a value of 6. I'm summing that together, so the quick way to do that is just say, okay, I just have 5 times 6, which is 30. Okay, so this is going to come up. Again, I know this is a bit confusing because there's nothing to really plug in there, but just know that it's this times this. Okay, that's all you're doing. Let me erase this. For the next one, I have C multiplied by A sub I. I'm just pulling C outside so I can calculate this sum first and then multiply C by that result. Okay, that's all it's telling me. These next two are very easy. Just think about the fact that you can split this up. So instead of having this written like this, you can split this up and have the A sub I here and then plus you'll have the B sub I over here. Same thing with subtraction. I have my A sub I here and my B sub I here. So this will come in handy, and I'll show you this in a moment when we do an example. These formulas are really going to come in handy. So if you're looking at the summation from I equals 1 to n of just I, okay, then it's equal to, you have n times the quantity n plus 1 over 2, okay? So we'll see an example of this in a moment, but you have this for I squared and also I cubed. So I encourage you, especially if you're going to get problems like this, if this isn't in your textbook, to pause the video and copy down these formulas or to search for these formulas on the internet, because they're very, very helpful. Okay, a lot of times there's no way you can get through what they're asking you to do in a reasonable amount of time without having these formulas. These are the shortcuts to make it happen. So let's look at our sample problem. And this one, you could calculate it. It's from I equals 1, okay, to 10. And we have this summation of 2i plus 5. Okay, so starting with 1, going to 10. So we know we could go, okay, 2 times 1 plus 5. Then 2 times 2 plus 5. And we can do this all the way until I gets to 10. But I don't want to do that. I'm going to show you a quicker way, and it's going to take a little bit longer because I'm explaining. But in general, it's going to be quicker to do this. So the first thing I'm going to do is just split this up. And again, I'm not good at drawing these things, but let me try. So I'm just going to go like this. And that's probably the best I can do. So let's say we have a 10 up here and I equals 1 here. And I'm just going to say that we have the 2i here and then plus. I'm going to make this symbol again, or attempt to. Let me just kind of do that. So the 10 here and the I equals 1 here and then a 5. Well, I already know, because I just looked at a problem like this, that this is going to be 50, right? I have a 5 here and a 10 here. If I go back up, we know we just saw this, right? So this is a constant, so it's just c times n. So we come back here, it's 5 times 10 or 50. So at this point, you can just erase this and replace it with 50, okay? You don't have to worry about it anymore. So now I just need to figure out what this is. Well, I can pull this 2 outside, okay? So I can move this outside, and I can calculate this. And remember, I just showed you the formula for that. So we have this n times the quantity n plus 1 over 2, okay? So let's go back down. So let me do this off to the side. So you have n, which is 10, right? So 10 times the quantity 10 plus 1 over 2. So 10 plus 1 is 11. So you would have 11. You would have 11 times 10. 11 times 10 is 110. And then divided by 2 would be 55. So you can go ahead and immediately erase this and put 55, okay? 55. And you're just multiplying by 2, so 2 times 55 is 110. So this is 110 plus 50, which is going to be 160. So a very quick and easy way to do this. It took us longer because I stopped and went back through the formulas. But again, once you go through and kind of, you don't have to memorize them exactly. You just have to remember which formulas you can use and then be able to reference them. And then you can use them very quickly in your homework, or hopefully on a test, your teacher will allow you to reference them and not have to memorize them. But even if you did have to memorize them, they would definitely be very, very effective for you, because you can find the summation of something like this very, very quickly. In this lesson, we want to talk about arithmetic sequences and series. All right, so we've already had a basic introduction to the concept of a sequence, and now we just want to go a little bit further, talk about something more specific known as an arithmetic sequence. So I want to start out with something very simple and then just get into the definition. So suppose we had this list of numbers here. We had -18, -8, 2, 12, and then we have these 3 dots. So this, again, tells me that the pattern is going to continue forever. So what is the pattern here? If I go from -18 to -8, notice that I'm adding 10. Now, if I go from -8 to 2, notice that I add 10 again. Then if I go from 2 to 12, notice that I add 10 once again. So in each case, I have this same number, okay, that gets added. Now, if I went from 12 to kind of the next term of that sequence, I would what? I would add 10, I'd get to 22, right? If I added 10 again to get to the next term, I get to 32, so on and so forth. So what we have here is an arithmetic sequence. And the reason we have this, let me just read the definition to you. Basically, a sequence where each term after your first term is going to be obtained by adding some fixed number to the previous term is known as your arithmetic sequence, or some people call it an arithmetic progression. Now, this fixed number, in this case it's 10, it's what we keep adding. This is known as your common difference, okay? And we express this with a lowercase d. So we'll put d is equal to, in this case, it would be 10. In most cases, when you're working with these, you can eyeball your list and figure out what the common difference is. Just in case you want to be real specific and use a formula, I have one that's probably in your textbook. So d, the common difference, is equal to a sub n plus 1 minus a sub n. So you've got to take 2 numbers in that list that are next to each other, and the order is going to matter here, okay? So what you'd want to do, if this is a sub n plus 1 minus a sub n, so let's just go back up here and just use an example. So d equals a sub n plus 1 minus a sub n. So let's say I took these two numbers. The numbers have to be next to each other. And what I'd want is for my a sub n plus 1, remember the way we order this, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4. So 2 is a sub 3. And then a sub 2 is negative 8. So I want the a sub 3 minus the a sub 2. Okay, just think about it in terms of this notation. Again, if you're just starting to work with sequences, this is a bit confusing. But essentially all I'm saying is that if this is 2, okay, if this is 2 plus 1, which is 3. Okay, that's all it is. So you always, if you're pulling two numbers out, just take the one on the right. In this case, that would be 2, okay, and subtract away the one on the left. In this case, that would be negative 8. That's all you have to do. So I would do 2 minus a negative 8. 2 minus a negative 8, and be careful there because you're subtracting away a negative. And this becomes 2 plus 8, which is 10, okay? Again, this formula is not super useful because you can eyeball that and clearly see the common difference is 10, but just in case you want to know what it is. Okay, let's jump in and look at an example real quick. So here we're given a sub 1, or the first term of the sequence, and it equals 1, and we're given d, the common difference, and this is 4. So we want to find the first 5 terms of the sequence. This is very easy. So we already know a sub 1 is 1, and then a sub 2, a sub 3, a sub 4, and a sub 5. So again, to get to each one of these, I take my first one and I add 4. Okay, so I take 1, I add 4, I get to 5. Then as I keep moving, I keep doing the same thing. Okay, so as I'm going through each one, I'm just taking the previous one and I'm adding 4. So 5 plus 4 is 9. 9 plus 4 is 13. 13 plus 4 is 17. If you wanted a sub 6, you would add 4 again and get to 21, so on and so forth. All right. So that's how you would go through and kind of figure out the first few terms of a sequence. But in some cases, you're going to be asked for the nth term of a sequence, okay? And you don't have to write out something, go through all of them until you get to it. What if somebody asked you for the 501th term, okay, for example? Well, here we have a general formula that we can use. So we have that a sub n is equal to a sub 1 plus d, your common difference, times the quantity n minus 1. So let's use this real quick with a little example. Let me just write this again. So we're going to put a sub n is equal to a sub 1 plus, you're going to have your d, your common difference, times the quantity n minus 1. Okay, so here we're asked to find a sub 37. Okay, so the 37th term of this sequence. And then we want to find a sub n. So this is the formula for the general term. And I'll show you how to do that. So I'm going to start with what I want to find. So I'm going to put a sub 37. Okay, so that's taking the place of a sub n here. This equals, what is a sub 1? It's 33. So I'm just plugging in. Then plus d, I'm given that, it's 2. Okay, then times the quantity n minus 1. What is n? It's 37. Okay, so it's what I'm trying to find. So it's 37. So 37 minus 1 is 36. This is all you need to do. This is very, very simple. Don't overcomplicate things. 2 times 36 is 72. And then 72 plus 33, we do 72 plus 33, which is going to be 105. Okay, so that's my answer for a sub 37. Let me just erase this and put this right here like this. Okay, so now let's talk about finding just a sub n. So this would be the formula for the general term in this sequence. And essentially all I'm going to do is just plug in. So I have a sub n is equal to, I know what a sub 1 is 33. Then plus, I know what d is, it's 2. And then times the quantity n minus 1. So you're just going to simplify this and that's it. Okay, so a sub n, let me just put a vertical bar there. So a sub n is equal to 33 plus 2 times n is 2n. And then minus 2 times 1 is 2. And then I can do 33 minus 2, that's 31. So I basically have a sub n is equal to 31 plus 2n. Okay, so we also talked about the fact that a series was when you added all the terms up in a sequence. Okay, so this is going to give you one single number. Now, generally speaking, a lot of times they're going to ask you for the sum of the first n terms of a sequence. Okay, so you're going to see this s sub n. So if this was s sub 9, I want to find the first 9 terms of that sequence and then find the sum. Okay, but we don't have to go through all of that because we have these little quick formulas we can use. So you have this one, s sub n is equal to n times the quantity a sub 1 plus a sub n over 2. So in this case, you have to calculate a sub n. Okay, so if this is s sub 9, you need a sub 9, okay, to make this formula work. With this one, you really don't need a whole lot. You just need your common difference and a sub 1, okay? So you don't have to actually calculate this. So let's look at an example. So we're given the following information. We have a sub 1, this equals 18. We have d, which is 5, and n, which equals 35. So basically what we're asking for here is the first 35 terms of this sequence, we want the sum of that. So this would be our arithmetic series here. So basically we're trying to find S sub 35. So this equals what? If I go back up and get my formula, let's use this one first, and then I'll show you this one. Okay, so this is n times the quantity a sub 1 plus a sub n over 2. So we have n, let me just kind of slide this down. So n times the quantity. You have your a sub 1 plus your a sub n over 2. Okay, so what's n? It's 35, so you can go ahead and plug that in. What is a sub 1? We know this is 18, okay? But what is a sub n? Well, you have to calculate that, and the way you would do that is you would use that formula that we just worked with. So we know if I go back, this formula here, let me just copy it. We'll use it real quick. So let me copy this and come back down. So in this case, because it's a little bit more work, you'd probably want to use the other formula. But basically, it's not too bad. So you would have a sub 35 would be equal to a sub 1, which in this case is 18. And then plus, you'd have d, which is 5, times the quantity, n minus 1. In this case, n is 35. So it would be 35 minus 1, which is 34. Okay, so let's multiply this. So 5 times 34 is 170. Then plus 18 is 188. So this guy right here, this a sub n, in this case, it would be a sub 35, this would be 188, okay? So we're done with that. So basically you'd have 18 plus 188, which is going to be 206. So you would have 35 times 206 divided by 2. Might as well just divide this by 2 now. And so you have 35 times 103, and that would give you 3,605. Okay, so S sub 35 is 3,605. So essentially, this is the result from adding the first 35 terms of this sequence. That starts with an a sub 1, that's 18. Okay, so that's your first term. And then your common difference is 5. So the next term would be 23, and that would be 28, so on and so forth. Now the other way, let me just show you the other formula. So we have S sub 35, and this equals, you have your n, which is 35, times, you would have your 2 times a sub 1. A sub 1 is 18, 2 times 18 is 36. And then you're going to have plus your common difference times the quantity n minus 1. Well, n here again is 35. 35 minus 1 is 34. So this is 34 times, in this case, d is going to be 5. And then this is all over 2. Okay, so 5 times 34 is 170. 170 plus 36 is, again, 206. We already know that 206 divided by 2 is 103. So we multiply this by 103. And again, we get 3,605. So either way you want to do it, both of these formulas are valid. This one is a little bit quicker in that scenario because you don't have to go through and calculate what a sub n is. So again, the answer here for S sub 35 would be 3,605. In this lesson, we want to talk about geometric sequences and series. All right, so in our last lesson, we talked about the arithmetic sequence. And with that guy, we found that each term after the first one can be found by taking the preceding term and adding some fixed number to it. Okay, the fixed number was known as the common difference, right? We represented that with a lowercase d. Well, now we're going to be multiplying, okay? And so let me give you the official definition. A geometric sequence, which is also called a geometric progression, is just a sequence where each term after the first is obtained by multiplying now the preceding term by a fixed non-zero real number known as the common ratio, and we'll use an r to represent the common ratio. So you can eyeball this and see what's going on. As I go from -4 to -24, I multiplied by 6. And this is going to be consistent. As I go from -24 to -144, multiply by 6. As we go from -144 to -864, we multiply by 6. So if you didn't see this by kind of eyeballing it, you could take two terms that are next to each other, take the term on the right, okay, and divide by the term on the left. So for example, if I took this term and this term, they're next to each other, take the one on the right, divide by the one on the left. So if I did -864 divided by -144, I would get +6, okay? And that's what this little formula is going to tell you here. So r equals, you've got your a sub n plus 1 over your a sub n. So if I kind of come back down here, if I write r equals, in this case, this is a sub 4 over, in this case, this is a sub 3, okay? So again, you take two that are next to each other, the one on the right, okay, that has a higher value for n is going to go in the numerator. The one on the left, the one that has a lower value for n, is going to go in the denominator, okay? And the same thing would go if I picked two other ones that were next to each other. Again, I could just take let's say this one and this one, if I did, in this case, this is a sub 3, right? A sub 3 over this one's a sub 2. Well, now I'd get negative 144 over negative 24. Let me put r equals this, and this would be 6 as well. All right, now the next thing we're going to talk about, you might also be asked to find the nth term of a geometric sequence. There's a really easy formula you can use for this. So a sub n is equal to a sub 1 times r, again, the common ratio, raised to the power of n minus 1. So again, this is going to match this. So let's look at an example real quick. So we're given this kind of list of terms here. We want to find a sub 9 and a sub n. So this is the formula for the general term, and this is a sub 9. Okay, so how do we do this? Well, let me just go back up here and grab this formula real quick. So a sub n equals a sub 1 times r raised to the power of n minus 1. So let me write that off to the side. So we have a sub n, okay, is equal to a sub 1, and then we're going to multiply this by r raised to the power of n minus 1. Okay, so let's start with a sub 9. So we have a sub 9 is equal to, let me make that a little better. And we know that a sub 1 is the first term from the sequence, right? This is a sub 1, this is a sub 2, so on and so forth. This is, let me go ahead and write this in. So this is a sub 3 and this is a sub 4. Well, we know that a sub 1 is 1. Then times, what's r? Well, again, I can just grab two terms that are next to each other. So let me grab a sub 4 and a sub 3. So again, if I grab this and this, I take the one on the right, the one with the higher index value, and I divide by the one on the left, the one with the lower index value. So r is equal to a sub 4 over a sub 3, which is negative 8 over 4, which is negative 2, okay? So I'm going to put negative 2 here for r. Now, this is very important. When you have a negative, you need to wrap it inside of parentheses. Don't put negative 2 like this, because negative 2, the negative and the 2 are raised to the power of n minus 1. So wrap it in parentheses, okay? Make sure you do that. Now, what is n minus 1? Well, in this case, again, n, this right here matches this right here. So 9 is what goes in there. So 9 minus 1 is 8, okay? So all we need to do now is just crank this out, and we're done, right? So negative 2 to the 8th power is going to be 256, right? Because, again, the negative and the 2 are inside of parentheses, so it's all raised to the 8th power. So this would be 1 times 256, which is just 256. So let me write this over here. So a sub 9 is equal to 256. Okay, so what about a sub n? And some people get confused by this because you're given this formula here and you're like, well, a sub n equals this. Well, no, you need to plug in things from the problem that you're given, right? So you need to plug in your a sub 1 and your r. Okay, so all I'm going to do is say that a sub n is equal to, my a sub 1 again is 1, and then times your r, in this case is negative 2. And if you don't want to put the 1 there, it doesn't matter, but I'm just putting it for completeness. So I'm going to put negative 2 here for my r, and then my n minus 1 here, okay? So whatever term you'd want to find, let's say you wanted the 10th term, plug in a 10 there, plug in a 10 there, evaluate, and you're good to go. Okay, so you can do that with any term of this sequence. Okay. Let's look at something a little bit more challenging. And I'm going to tell you there's lots of ways to solve these. I'm going to show you the way that I do it. This is the quickest way that I've found, but if you have a better method, that's fine too. So we have a sub 3 equals 48 and a sub 6 equals negative 3072. We want to find a sub 9 and a sub n. So let's start with a sub 9. Now, we don't have two terms that are next to each other, so we can't do the formula for r that we're used to. But we can kind of look at our general formula. So we know that a sub n is equal to, we have a sub 1 times our r raised to the power of n minus 1, okay? So what I want to do is just plug some things in real quick, and I'm going to show you that you can basically set up a system with two equations and two unknowns, and you can solve for what you need, okay? And again, there's other ways to do this, but this is how I'm going to do it. So I'm going to plug in for a sub 3, just to show you all the steps. I'm going to put a sub 3 there. This would be a 3. 3 minus 1 would be 2, okay? And I know what a sub 3 is. It has a value of 48. Okay, so let's put that right there. So now we have 48 equals a sub 1 times r squared. Okay, for this one, I'm going to do a sub 6. So I'm going to do a sub 6. And I'm just going to skip that step and plug in a negative 3072. And again, this would be a 6. 6 minus 1 is 5. Okay. Two equations, two unknowns, right? I need to find out a sub 1, I need to find out r. So let me solve one of these guys for a sub 1, okay? And I'm just going to solve this top one. So I'm going to say that a sub 1 is equal to what? I would just divide both sides by r squared. So 48 over r squared. Okay, so now I can take this, which is a sub 1, and plug it in there. Okay, that's all I've got to do. So I've got negative 3072 is equal to 48 over r squared times r to the 5th power. Okay, let me just erase all this, get this into a cleaner format. I can go ahead and get rid of this and say this is to the 3rd power. Okay, and so what we'd have is what? 48r cubed is equal to this negative 3072. We'll divide both sides by 48. And we're going to get that r cubed is equal to negative 64. If I take the cube root of each side, let me make sure I put a 3 there. What am I going to get? Well, this on the left would be r, and on the right, I would have negative 4. So I know r is negative 4. So let me just write here off to the side, r equals negative 4. Well, I still need my a sub 1, so let me erase this real quick. We had that solved for a sub 1, so let me just do that again. We know that a sub 1 is equal to 48 divided by r squared. Well, we know that r is negative 4, so negative 4 squared, again, if I'm plugging something in here and I'm squaring, I want the negative and the 4 wrapped in parentheses because it's negative 4 that's being squared, okay? So don't make that mistake. So this would be negative 4 squared, so this is 48 over negative 4 squared is 16, and 48 over 16 is 3, okay? So now I have my a sub 1 and I have my r, so I'm ready to go through and find my a sub 9, okay? So my a sub 9, again, if you use the formula, let me just write this out. So a sub n is equal to, you've got your a sub 1 times r raised to the power of n minus 1. So we know a sub 1 is going to be 3. And we know that this is a 9 here, okay? And we know this is a 9 here. Let me make that a little bit better. We know this is a 9 here. 9 minus 1 is going to be 8. So what is r? It's negative 4. Let me erase this and put negative 4 raised to the 8th power. Again, if you have a negative there, make sure you wrap it in parentheses. All right, so this answer is going to be really big. If I punch that up on my calculator, I get 65,536. So we'll say a sub 9 equals 3 times. Again, that was 65,536. And then we'll just do this multiplication, and that'll give me 196,608. Okay, so that's my a sub 9. So a sub 9 is equal to 196,608. Okay, so a sub n is really easy to do. Okay, so a sub n, let me just write this down here. So a sub n equals what? Again, it's a sub 1, which in this case is 3, times your r, which in this case is negative 4, raised to the power of n minus 1. All right, so now let's move on and talk about some of the problems you'll get with geometric series. So this first one is where we're just summing the first n terms of a geometric sequence. Again, this would be a geometric series. So you have your s sub n. Remember, the n here is the value that you're kind of stopping at. So if it was s sub 10, well, then I want to sum the first 10 terms of that geometric sequence. So basically to do this, you have your a sub 1 here multiplied by 1 minus r raised to this power of n. Again, you got the same number there and there. And then it's over 1 minus r. Okay, so a real simple formula to use. And let's go down here. And we've written this in summation notation. Hopefully you remember how to use this, how to read this. This is from n equals 1 to 8. It's the summation of 3 times, you have your negative 2 raised to the power of n minus 1. So essentially, the formula here for the geometric sequence, it's a sub n equals 3. Okay, that's going to be your a sub 1. And then times your negative 2, that's your r, raised to the power of n minus 1. So again, this is your a sub 1, and this is your r. Okay, so if I want to use that formula, let me go back up to it for a minute. And you can copy this down real fast, and I'll go back down. If you want to use the formula, what I'll say here is that s sub 8, right, because I'm going to that number there, is going to be equal to what? Well, I'm plugging in, let me just kind of write this formula out. So it's a sub 1 times, it's 1 minus r raised to the power of n. Okay, so let me stop and fill this out. So r we know is negative 2. It's negative 2. And we know that n, in this case, is 8. Okay, so I'm going to put 8 here. And let me just close that down. And then this is over. Let me fill in a sub 1. That's going to be 3. So let me put that there. It's over your 1 minus r. So your 1 minus, in this case, r again is -2. Okay, so let me copy this real fast. And let me just paste this in so we have some room to work. Okay, so this is pretty easy. We're just evaluating things. So s sub 8 is equal to, we have 3 times. If I did -2 to the 8th power, we know that's 256. And then we have 1 minus that, okay? And this is over 1 minus the -2, which is 1 plus 2, or 3. Well, before I do anything, remember this is 3 times this amount here. This can be canceled, right? Because this is multiplication. So I end up with just 1 minus 256, which is -255, okay? So the sum of the first 8 terms of that geometric sequence would be -255. All right, so the last thing I want to talk about would be the sum of the terms of an infinite geometric sequence. And basically this formula I'm going to give you here is valid as long as the r that you're working with is greater than -1 and less than 1, okay? If the absolute value of r is greater than 1, then what's going to happen here is you just write that you don't have a sum, okay? So what we're going to do is just go through this real quick. So this is s sub infinity. So as you keep summing these terms of your sequence, as you keep going forever and ever and ever, as you approach infinity, you get a value of a sub 1 over 1 minus r. Okay, so pretty easy to work with this formula. Let's look at an example. So we have the summation from k equals 1 to infinity of -4/3 times this 1/5 raised to the power of k minus 1. So again, this is your a sub 1. This is your r. Okay, so when you look at your r value, is it greater than -1 and less than 1? Well, yeah, this is 1/5. So this falls in the category where we're going to get an answer from this formula. So what we're going to do is just write this out. Let me just kind of see if I can fit this on the screen. My formula again, s sub infinity is equal to, you've got a sub 1, which in this case is -4/3, okay, over, you've got 1 minus r. So 1 minus 1/5. So let me copy this. Again, we're just going to run out of room here. There's just too much stuff on the screen. Okay, so the fastest way to solve this is just to find the LCD of all the denominators. So you've got a 3 and a 5. So your LCD is going to be 15. So I'm going to multiply the top part by 15 and the bottom part by 15. So I'm just multiplying 15 by -4/3. Of course, the 15 would cancel with a 3 and give you a 5. 5 times -4 is -20. Let me write that down here so we have some room. Then 15 times 1 would be 15. And then minus, if I did 15 times 1/5, the 15 would cancel with the 5 and give me a 3. 3 times 1 is 3. So 15 minus 3 is 12, okay? And we know that there's a common factor here of 4. So if I divide this by 4, I get 5. If I divide this by 4, I get 3. So the answer here would be -5/3. In this lesson, we want to talk about the binomial theorem. All right, so before we jump in and talk about the binomial theorem, we need to understand some different notation that we're going to come across. And we're going to start with this factorial notation. So if you see something like 5 factorial, okay, what this is telling you to do is to start with this number 5. And then you're going to multiply, okay, by each number going down by 1 until you hit 1. Okay, so what this means is I start with 5. And again, I multiply by each number going down by 1. So I go down by 1 to 4. And then down by 1 to 3, and then down by 1 to 2, and then down by 1 to 1. So each number until I get to 1. Just keep going down by 1. That's all you're doing. So you can crank this out really quickly, or you can use your calculator. You will have this button available to you. As long as you're using like a scientific calculator, something like a TI-83 or 84 or whatever it is now. But basically, you do 5 times 4 is 20, times 3 is 60, times 2 is 120, then times 1 is 120. Okay, so that's pretty easy. Then when we get to 7 factorial, okay, we're going to do the same thing. We're going to start with 7, and I just keep going down by 1. So I'm going to go down by 1 to 6, then 5, then 4, 3, 2, 1, so on and so forth. So you can crank this out manually, or again, you can hit the key on your calculator, and basically it's going to give you 5,040 as an answer. So now that we understand the factorial notation, it's time to look at a formula we're going to use today for the binomial coefficients, okay? So we're going to see this more in depth in the next lesson when we talk about combinations. But for right now, we're just going to take it as a given, okay? So we have this little n choose r. Okay, so that's how this is written. You might see a different type of notation. You might see this lowercase n, an uppercase c, and a lowercase r like this. So this and this, it's the same thing, just different notation. Okay, I prefer to use this one, so that's what we're going to go with. So this is, again, n choose r, and it's equal to n factorial, okay, over, you have your r factorial times the quantity n minus r factorial, okay? Let's see an example real quick. So I have 10 choose 6. So again, you could also write this as 10, and then you have the c, and then the 6 like this, okay? So a 10, a big C, and a 6. So this is 10 choose 6. That's how that's read. In this notation, it's read the same way. Again, the same thing, different notation. So 10 choose 6 is equal to, again, I take this number here, whatever this is, it's going to go here, and it's going to go here. Okay, so I've set that up already. Then this number here goes here and also here. Okay, so it's pretty easy to remember once you do it a few times. Just something you need to work through a few examples with. So let's go ahead and crank this out real quick. I just want to say on your calculator, you have this button available to you as well. You would hit 10, and then you would hit the NCR key like this. It's a lowercase n, an uppercase C, a lowercase r. And then you would follow that with a 6 and hit enter, and it will give you an answer. Okay, and I'll give you that answer in a minute. Let's just work it out. So what I'm going to do here is go ahead and say 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you see why a calculator is handy here, right? And then you have 6 factorial. So let me write that under here because it's going to cancel. 6 times 5 times 4 times 3 times 2 times 1. 10 minus 6 is 4, so 4 factorial. So let's write that over here. 4 times 3 times 2 times 1, okay? So we know that, let me just pick a different color here. This will cancel with this. So that's gone. And you can erase it, but I'm just going to leave it there for completeness. And then you can start canceling things here. So 10 divided by 2 is 5. 9 divided by 3 is 3. 8 divided by 4 is 2. And then really nothing else we can cancel. So let's just write here that we have 5 times 3 times 2 times 7. Okay, everything else is gone. And if we punch this up on a calculator, 5 times 3 is 15. 15 times 2 is 30, and then 30 times 7 is 210, okay? And again, you can get this more quickly by just using the n choose r key on your calculator. Okay, now let's move on and talk about the binomial theorem. So what is this used for? It's used to expand something like the quantity x plus y to the 4th power. So we already know to kind of work with this, we would go x plus y, okay, times x plus y, times x plus y, and then times x plus y. Okay, so if we went through and used, FOIL, and then after we had, more terms, we would just keep going using the distributive property. But this would take a really, really long time. So the binomial theorem is going to allow us to find our answer here really, really quickly. Okay, so there's a lot of different techniques and strategies that go with this. I'm just going to give you what I've learned over the years. I'm not going to go through the book formulas because I feel like they really confuse you. So basically the first thing is, in your book, it's going to call this exponent here n, okay, in most cases. So let's just say this is n. So we'll start by saying there's going to be n plus 1 terms, okay? So if this exponent is a 4, you're going to have 5 terms. If it was a 7, you'd have 8 terms. If it was a 12, you'd have 13 terms, so on and so forth. So we know there would be 5 terms. So let me just put 5 spaces here. So a space, plus a space, plus a space, plus a space, plus, and then a space. So 1, 2, 3, 4, 5. This is how I always do it. Now, the next thing is you are going to take whatever is in this first position and you're going to raise it to this power, and that's going to go right here. Okay, so this would be x to the 4th power. Then you're going to take whatever's in this position, okay, and you're going to raise it to this power, and you're going to put it in the last position, okay? So this is easy to remember because you're basically saying, okay, this to this is first, right? It's in the first position, goes in the first position. This to this is in the last position. It's in the last position, goes in the last position. So that's the first thing you want to do. Now, the next thing is really simple, really easy to remember. The exponents on your variables, as you go to the right, okay, or as you go to the left, they're changing by a value of 1. Okay, so what do I mean by that? So my exponent on x is going to decrease by 1 as I move to the right. So this is going to be x cubed, then it's going to be x squared, then it's going to be x to the 1st power, and then here it would be x to the power of 0, which is just 1, so we don't write that. Now the same thing goes for our y. So now we're going this way, so we would say this is y cubed. We would say y squared. We would say y to the 1st power, or just y. And here again, it would be y to the power of 0, or just 1. Okay, so you don't have to write that. Now, though either way you look at it, as you go to the right, okay, everything is changing by 1. So this went down by 1, down by 1, down by 1, okay? And this went up by 1, up by 1, up by 1. okay? So I started with y to the power of 0. Now I've got y to the power of 1, y squared, y cubed, y to the power of 4. So you see the pattern there, okay? Really easy to remember. Okay, so once you have the kind of variable parts worked out, and in some cases you're going to have coefficients here, so it'll be a little bit more complicated. But once you have this part worked out, the next part is kind of the tricky one, okay? So you need to find the coefficients. Now, you can work with the combination formula that we just talked about, and I'll show you that in a minute, or you can use Pascal's triangle. So let's do a little side note here. We're going to come up here and look at Pascal's triangle. So you'll see this in your book. The main thing to remember, if you don't remember anything else about this, is that this is row 0, okay? Everyone makes a mistake on that, okay? You need to know the rows. This is 0, this is 1, this is 2, this is 3, this is 4, this is 5, okay? So it starts with row 0. So what you want to do is find the kind of row that corresponds to that n value or that exponent. Again, that's right here. So if this is a 4, then when I look at this, I want the 4th row. But again, I'm starting with 0. So really it's the 5th row if you're thinking about it as starting from 1, but all the books start with 0. So it's 0, 1, 2, 3, 4. Okay, so I want this row right here. Let me highlight it for you. So I'm going to take a 1, a 4, a 6, a 4, and a 1. So let me just copy that real quick. I'm going to come back and I'll explain this in a minute. So let's just paste this real quick. And I'm just going to show you how quickly we can be done. The 1 and the 1, everything just goes in order, right? So the 1's on the ends, we don't need to write that because 1 times anything is just itself. This would be a 4, and this would be a 4. Okay, so notice how the second term and the second to last term, those are the same. And the middle term is just a 6. Okay, and just that quickly, we're done. We've expanded this guy. We know that it's x to the 4th power plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the 4th power. Now, let me go back and do a little bit of explaining on this Pascal's triangle because you might be saying, what in the world is this thing? Basically, the way this thing starts is, you notice you have a 1 at the top, then you have 2 1s here, okay? And basically, as you keep going down, as you go down the sides, notice everything's a 1, everything's a 1, okay? So on the outsides, everything's a 1, okay? But as you get into the middle stuff, and let me just kind of erase this real quick. As you get into the middle stuff, think about this number 2. Where does that come from? It comes from the sum of this plus this, okay? So go up to the top left and to the top right. If I look at, let me just kind of erase this. If I look at 3, it's the sum of go to the top left and the top right. So those two numbers, right? So 1 plus 2 is 3. This guy, same thing. 2 plus 1 is 3. This 4 here, 1 plus 3 is 4. This 6 here, 3 plus 3 is 6. This 4 here, 3 plus 1 is 4. You know, so on and so forth. So you can draw this thing out yourself, okay, by remembering that pattern, but it's just going to be your preference, right? I'm going to show you a different way to do this. If you have a lot of problems to work through and you're just doing homework, or maybe you're on a test and they let you use this thing, well, I would just use it, right? Because it's a lot faster than what I'm about to show you. Now, let me erase these coefficients and pretend that we don't have them, okay? So if we don't have them, how else can we get them? Well, basically what you would do is you would use that combination formula that I just talked about. And you're always going to take this number right here, this 4, okay, the n value as we say, and we're going to put that on the top. And let me just kind of slide this down because I'm not going to have enough room. You're going to take the coefficients. I'm just going to write it down here. So it will be 4, and you basically always take the exponent that's on y, or this second value. So in this case, the exponent on y is 0, so it would be 0. And then your coefficient here would be 4 choose 1. This one would be 4 choose 2. This one would be 4 choose 3. And this one would be 4 choose 4, okay? Now, these on the outsides are always going to be 1, so you can just get rid of them, okay? You don't need to crank that out. Again, you can use a calculator for this. If you do 4 choose 1, you're going to get 4. And if you do 4 choose 3, you're going to get 4. So I get a 4 here and here. And we can erase this. If you do 4 choose 2, you're going to get 6. Okay, so you do this there. Now, even if you're using a calculator, it is going to be a little bit slower versus having Pascal's triangle. Because again, with Pascal's triangle, I can just go up here. I can grab things again. This is row 0, row 1, row 2, row 3, row 4. I can just grab the coefficients and I'm done. Okay, I don't have to do anything. So it's just a matter of a personal preference in terms of what you want to do. Okay, let's look at a harder example, or I would say not harder, more tedious. So here we have x plus 3y raised to the 4th power. Let's go ahead and set this up. I know I would have 5 terms, right? I know I would have 5 terms. So 1, 2, 3, 4, 5. Okay, I would take this guy, raise it to the 4th power. And then as I go to the right, I'm decreasing it by 1. So x cubed, x squared, x to the first power. And again, this is x to the power of 0, but you don't have to write that, right? That's just 1. Then I would take, again, you've got to be very careful here because whatever's in this position is raised to the 4th power. So now you have a number involved, okay, not just a variable, so you got to be really, really careful. You would start here with 3y to the 4th power, okay? Then here it would be 3y cubed. Then here it would be 3y squared. Then here it would be 3y to the first power, and here it would be 3y to the power of 0. Again, that's 1, so we don't write it. So if we simplify this, we just kind of write this beneath here. So far we have x to the 4th plus, this would be 3 times x cubed y, and then plus we would have 3 squared is 9, so this would be 9x squared y squared. And then plus 3 cubed is 27. So that would be 27xy cubed. And let me kind of slide this down because we're going to run out of room. And then plus we would have 3 to the 4th power, which is 81. And then y to the 4th power. Okay, let me just erase this. We're just going to keep adding to this. We just need our coefficients now. And again, we just work with something that was raised to the 4th power. So you should remember that the coefficients are 1, 4, 6, 4, 1. Okay, so basically, again, on the outside, you can get rid of it. Here, I need to multiply by whatever's there. So 4 times 3 is 12. So this would be 12. And 6 times 9 is 54. So this is 54. 4 times 27 is 108. So let's put 108 there, and we're done. Okay, so again, if you're using this Pascal's triangle, you just go to the 4th row. Again, it starts with 0. I can't say that enough because a lot of students, they make that mistake and say, this is the 4th row, right? The one that's labeled with a 3. Okay, you want to go to the 4th row, grab those coefficients, and then just punch those in. Again, if you don't want to do it that way, you can use the combination formula. So again, you start with this. So it's 4, choose 0. Then it's 4, choose 1. Then it's 4, choose 2. Then it's 4, choose 3. Okay, then it's 4, choose 4, okay? And basically, if you crank all these out on your calculator, you're going to get the exact same answer, okay? So our result here is going to be x to the 4th power plus 12x cubed y plus 54x squared y squared plus 108xy cubed plus 81y to the 4th power. So for this one, I have 3x plus 2y. This is raised to the 5th power. So again, now this guy is going to be 5. Okay, so I'm going to have 6 terms, right? So it's always this number, which again, we call this n. So n plus 1. So here, n is 5. So 5 plus 1 is 6. So you're going to have 6 terms, and I'm not going to space it out. I'm just going to kind of do it. I'm going to take this guy and raise it to the 5th power. So 3 to the 5th power is 243. And then times x to the 5th power. Then you would have plus, you would have, let's just go down. We would have 3x raised to the power of 4. So 3x raised to the power of 4. 3 to the 4th power is 81. So you would have 81 x to the 4th power. And then plus, I'm going down by 1. So now I would have 3x cubed. So 3 cubed is 27, then x cubed. Then plus, let me just kind of drag this down here, okay? So I'm going to do 3x squared, so that would be 9x squared. Then plus, I would have 3x, right? It would be raised to the 1st power. And then lastly, you would have your 3x raised to the power of 0, which is just 1. Okay, so you can leave that off. Now this guy right here, again, I take 2y, I raise to the 5th power, that goes last. So 2 to the 5th power is 32, so that would be 32y to the 5th power. And then as I go this way, I would have what? 2y to the 4th power. So let me write this up here. So 2y to the 4th power. I know this gets real messy. 2 to the 4th power is 16. And then y to the 4th power. So you're going to have to multiply here. So 16 times 3 is 48. So you would have 48 x y to the 4th power. Okay. And then as we move this way, now I'm working with 2y cubed. So 2 cubed is 8. So this would be 8y cubed. So 8 times 9 is 72. So you would have 72 x squared y cubed. Okay. And then as I move up here, now I'm going to have 2y being squared. So that would be 4y squared. So let me just write y squared there. 4 times 27 is again 108. Let's write that in. And then as we go here, now I'm going to have 2y to the 1st power. So I'll just put a y there. 2 times 81 is 162. And then here we don't need to write anything. You'd have 2y to the power of 0, which is just 1. Okay, so again, you can go through to get the coefficients. You would start with 5 choose 0, which is 1, so you can leave that off. And then you would go to 5 choose 1, and then 5 choose 2, and then 5 choose 3, and then 5 choose 4, and then finally 5 choose 5. Okay, so this would be 5 choose 0, which is 1. This would be 5 choose 1, which is 5. Okay, so I'm just going to put a 5 there. This would be 5 choose 2, which would be 10. Then for 5 choose 3, you would get 10 again. And then as we get 5 choose 4, it's always going to match this. So this is going to be 5. Then as we get to the end, we have 5 choose 5. Again, 5 choose 5 and 5 choose 0. Those are each going to be equal to 1. So you can get rid of those. Okay. So let's just get rid of this and let's do our multiplication. So this stays unchanged. 5 times 162 is 810. So 810. 10 times 108, let me just slide this down, would be 1080. So 1080. And then 10 times 72, let me just slide this down real quick. 10 times 72 would be 720. So this would be 720. 5 times 48 would be 240. So 240, and that's it, we're done. So we get 243x to the 5th power plus 810x to the 4th power y plus 1080 x cubed y squared plus 720x squared y cubed plus 240x y to the 4th plus 32y to the 5th power. Now again, if you wanted to use this row here, row 5, that's fine. You have 1, 5, 10, 10, 5, and 1. Again, what we just saw. All right, so let's wrap up the lesson and talk about how to find a specific term. Some books will call this finding the kth term of a binomial expansion. So let me just read this problem and I'll give you a simple little formula that you can use. So we have the quantity x plus 2y to the 7th power. We want to find the third term. So you could use the binomial theorem, okay, and kind of write all the terms out. You'd have 8 of them, right? Because this is a 7, so you'd have 8 terms. And then go through and get the third one, right? But that would be kind of a waste of time because you have this little simple formula that you can use. So what I'm going to give you is I'm going to say that this is n. Again, I always refer to that exponent as n. This 3 here is going to be a value of k. Okay, that's what we're going to call it. So if you were finding the third term, k is 3. If you were finding the 10th term, k is 10. If you were finding the 21st term, k is 21. Okay, so on and so forth. So what you're going to say is that the coefficient is n choose k minus 1. Okay? So in our case, n is 7. So n, let me write this here. So n is 7. And then k is 3. So 3 minus 1 is 2. So you can have 7 choose 2. That's the first part. Then times. You're going to have the x, which is whatever's in this first position here, raised to the power of n minus the quantity, okay, k minus 1. So this is inside of parentheses here, so be very, very careful to just plug in and evaluate it with it inside of parentheses, okay? So if I plug in and say this is x raised to the power of 7 minus the quantity, okay, you would have 3 minus 1. Okay, so this is going to be what? It's going to be 7 minus 3 minus 1 is 2, right? Because you do what's inside of the parentheses first. So you would have 7 minus 2, and 7 minus 2 is 5. Okay, so that part's done. Then we would have y raised to the power of k minus 1. Now in this case, for our y, what's our stand-in? We have 2y, right? So you have to take whatever's in that second position, okay, and do this to it. So I'm going to take this and say it's times 2y raised to the power of k is 3 minus 1. So 3 minus 1 is 2. So this would be squared. So if I square 2, I get 4. And if I square y, I get y squared. So this would be 4y squared. Okay. And then I have 7 choose 2. Let's just go ahead and do that. You punch that into your calculator, you get 21. So you'd have 21 times 4, which is 84. So you'd have 84x to the 5th power y squared. Okay. Let's look at one more of these. Let's try to do it without the formula. I'm going to reference it. But basically, we have y plus 2x raised to the 6th power. Okay, we want to find the fourth term. So again, just think about this in your head. This is k, and this is n. Okay, so just get used to that and just basically say, okay, what do I need to do? I want to do n, so this number right here, k, which in this case is 4, minus 1. So 4 minus 1 is 3. So 6 choose 3. So that's the coefficient part. Then what's this part here and here? Well, remember, I take this guy, okay, so I take this guy, in this case it's y, and I raise it to the power of n, which in this case is 6, minus, and this is important, you use parentheses, the quantity k minus 1. So 4 minus 1, okay? So 4 minus 1 is 3, okay? So we're going to have 6 minus 3. So 6 minus 3, which is 3. So we'll put y cubed here. Then the next part is going to be this guy. So it's going to be times, you have your 2x raised to the power of, again, k minus 1. So in this case, k is 4. 4 minus 1 is 3. So 2 cubed is 8, and x cubed is just x cubed. So we put times 8 times x cubed. Okay, so let's do 6 choose 3 real quick. And that is going to give us 20. Okay, so this is 20. And so what we would say is 20 times 8 is 160. So I can write this and say this is 160. Okay, let me just erase this as I go. Times y cubed x cubed. So that would be your fourth term when we expand this. In this lesson, we want to start talking about sets. Let's start out by just giving a basic definition for a set. So a set is just a collection of things, or you could say a collection of just some stuff. Now, it should be clear whether something belongs to the set or not. Now, generally speaking, when we're talking about an algebra class, when we talk about a set, we're talking about a collection of numbers that fit a certain profile, or you could say a collection of numbers that fit a certain definition. So as an example, let's start out by just thinking about the whole numbers. So this is a set or a collection of numbers that fit a certain profile. They start with the number 0, and they increase in increments of 1 indefinitely. So generally, when we list the whole numbers, we'll start with 0. We'll go 0, 1, 2, 3. At some point, we're going to stop because we can't list every whole number. That's impossible. And we'll put 3 dots. Now, when we think about this in regards to being a set, we have some more definitions involved. So the numbers that are listed here are known as the members or elements of the set. And like I said, it should be clear whether something is in the set or not in the set. So as an example, if I asked you, is -5 a member of the set of whole numbers, you would say no, because the whole numbers start with 0 and increase in increments of 1 indefinitely. So that doesn't fit that profile or that definition. So it is clear that -5 is not a member of that set. Now, another thing that we do when we have sets, we enclose our members or elements inside of set braces. So we're going to enclose this inside of set braces. So these are set braces, okay, if you hear that. And the last thing I want to say here is that the method that we're using here is known as the roster method. Okay, this is known as the roster method. And basically what we're doing is we're listing the members or elements of the set inside of set braces. So that's the roster method. As another example, let's say we talked about the set of integers. Okay, the set of integers. So the set of integers, if I use the roster method again, inside of set braces, I would have 3 dots coming this way, comma. I'd start with something like, let's say, -2, then -1, then 0, then 1, then 2, then comma, and then again, I'm going to put 3 dots. And again, in case you don't know what the 3 dots are, they're known as an ellipsis, and they just tell you that the pattern is going to continue. So going this way, I know that I'm decreasing by 1. So after -2, I'd have -3, then -4, then -5, so on and so forth. This way, after 2, I'd increase by 1. So I'd have 3, then 4, then 5, so on and so forth. So this is the set of integers. And again, it's clear whether something's in that set or not. If I gave you the number 0.675, it's clear that that's not an integer. It's not in that set. Now, although generally in algebra we're going to have sets that involve numbers, we can have sets that don't involve numbers. So let's say as an example I had a set that contained the first 5 letters of the alphabet. Well, again, using the roster method, I would list A, B, C, D, and finally E, right, the first 5 letters of the alphabet, inside of my set braces. All right, so now that we have the basics under our belt, let's talk about a couple of other things. So the order that we list the elements of a set is not important. So let's say, for example, I have a set whose elements would be 1, 6, and 7. This would be equal to the set whose elements would be, let's say, 6, 7, and 1. And it's also equal to the set whose elements would be 1, 7, and 6, as an example. The order is not important. What's important are the elements or the members of the set. If this set contains 1, 6, and 7, and this set contains 1, 6, and 7, and this set contains 1, 6, and 7, they're equal because the members or elements are the same. As another example of this, let's think about the states that border Louisiana. Okay, my home state is Louisiana, and so the states that border it are Mississippi, Mississippi, okay, kind of hard to spell. Then Arkansas, and Texas. So this is the set whose elements are the states that border Louisiana. And this would be equal to the set with the same elements just reordered. So let me reorder this. Let me write Texas first, then write Mississippi, Mississippi, and then let me write Arkansas last. And again, I could change the order as much as I want. What's important here are the elements or the members of the set. All right, so generally speaking, we can use capital letters to name a set. So we want to let A be the set of whole numbers less than 4. So we know the whole numbers start with 0 and increase in increments of 1. So I will put a capital A out here, and this equals inside of set braces. So again, the set of whole numbers less than 4 start with 0, then 1, then 2, then 3. It's less than 4, so I'm not going to continue after that. So this is my set A. Again, that's got the elements 0, 1, 2, and 3 involved. All right, so another big one that you need to know is a set that contains no elements is referred to as an empty set or null set. So once we get into Algebra 2, we're going to start using something known as solution set notation. And a solution set is nothing more than a set whose elements are a solution to your equation. So as an example real quick, let's say you had something like 2x minus 5 is equal to, let's say, 27. So add 5 to each side of the equation. That would cancel. You get 2x is equal to 32. Divide both sides of the equation by 2. You get x is equal to 16. So to write this in solution set notation, I just literally put 16 inside of set braces. That's all it is. This is a solution set. This is a set whose elements are a solution to the particular equation that you're working on. And this isn't particularly that useful when you get into Algebra 2, but if you get into higher levels of math where you solve something and you got a bunch of solutions, it's just a neat and clean way to organize your solution. Okay, that's all it's used for. But we sometimes get equations that can't be solved. Okay, it'll have no solution involved. So a set that contains no elements is referred to as an empty set or null set. So what we're going to do is, if we have an equation with no solution, we're going to use this symbol right here to denote that, because that particular solution set has no elements, right? So if it has no elements, it's the null set or the empty set. So you can use this symbol here for that, or you can also use set braces with nothing inside. But one thing I want to warn you of, and this is a big thing when you get to college math, do not do this. This is wrong, okay? Write that down. It's a very common mistake that students make. Do not put this symbol inside of this. You don't want to do that. That is the set that contains one element, and that element is the empty set. And I don't want to go into set theory and start confusing you, but just know that it's wrong, okay? You can use this symbol or you can use this symbol, but you cannot combine the two. So as another example of this, let's say I said let B be equal to the set of all pigs that are living on Saturn. Now, I've never been to Saturn. Chances are you've never been to Saturn. But I'm going to say that there are no pigs that live on Saturn. So that set would be an empty set, right? That set would contain no elements. So we can say that this set can be denoted by the symbol for the empty or null set. Or you could also say B is equal to this. But again, you cannot say that B is equal to, inside of set braces, placing this symbol in there. That, again, is wrong. That is wrong. Do not do that. No. All right, so the next thing is that this symbol here, which if I draw it, let me draw it. It looks like a sideways U, and then you just put a line down the center there. So the symbol here is used to denote is a member of the set. So as an example, we have set Z, and Z is equal to, we have the members 3, 7, 1, and 8. So what I can do is I can take each one, and I can say, okay, 3 is an element of set Z. It's denoted like that. Or I could say 7 is an element of set Z. Or I could say 1 is an element of set Z. Or lastly, I could say 8 is an element of set Z. Now similarly, the symbol here, basically we just put a line through the other symbol, is used to denote is not, let me highlight that, is not a member of the set. So with the same set Z, with the members 3, 7, 1, and 8, I could do something like this. I could say something like 6 is not an element of the set Z. I could really use anything I want other than these 4 numbers. I could say 0 is not an element of set Z. I could say negative 32 is not an element of set Z. So on and so forth. So another important concept would be that of the universal set. So this one's a little bit difficult to wrap your head around at first, but something after you practice a few of these that you really can understand. So the universal set, which is generally denoted with a capital letter U, is a set that contains all elements under consideration. Now, if we're talking again about the states that border Louisiana, let's just name this for the purposes of this example here. Let's name this as set A. So set A has the elements that fit this profile where they're states that border Louisiana. So we already know that this would be Mississippi, Mississippi. We know it would be Arkansas. And we know that it would be Texas. Okay, so 3 elements in this set. But if we think about the universal set here, what are all elements under consideration? Well, we're talking about states in the United States of America. So all elements under consideration would be all of the states in the United States of America. So the universal set here would contain every state. Now, we're not going to list all of them. That would be very time-consuming. But in alphabetical order, we could just start with 2 of them. So in alphabetical order, it would be Alabama. Then it would be Alaska. And let's put our 3 dots there. And let's finish up with the last 2, which would be Wisconsin and then Wyoming. Now, as another example of the universal set, let's say we're again talking about the United States. So the United States has a president. We all know this. And we could talk about a set, and let's call it set A again, whose elements are the presidents that are currently living. Now, this set would change over time. We're filming this video in 2015. So in 2015, the living presidents, we would have Jimmy Carter. We would have George Bush Sr. So let's just put G period B period. And we'll put number 1 because he was the first George Bush to be president. Of course, his son would be George Bush II. So then comma, after him we have Bill Clinton. And then comma, we're going to have George Bush number 2 or George Bush Jr. So G period, B period, and then 2. And then we're going to have Barack Obama. And to fit this on the screen, I'm just going to put B period, O period. And then we're going to close up with some set braces at the end. So these are all the living presidents as of 2015. Now in 2016, we're going to have a presidential election. So for sure it's not going to be Barack Obama because he's going to be out of office. So we'll have another president to add to this list. But as people pass away, as new presidents get elected, this set would change over time. But what's important is to understand that the universal set, the set with the capital letter U, would be what? It would be all of the U.S. presidents that ever existed. Okay, so we would start with George Washington. So George Washington. And then the next one was John Adams. And then, of course, after that, you had Thomas Jefferson and so on and so forth. So let's just put 3 dots here. And we'll kind of come in with the final 2. We had George Bush number 2, or George Bush Jr. And then we had Barack Obama. And again, it could be whoever in the next election that wins. So this list would be added to. If Donald Trump wins, if Hillary Clinton wins, if somebody else wins, we'll have another president to add to both lists. All right, so additionally, we have finite sets, which have a specific number of elements. And then we have infinite sets, which have an unlimited number of elements. So as an example of a finite set, let's say I told you that we had a set A, which was the whole numbers that were less than 6. So this would be 0, 1, 2, 3, 4, and then 5. So that's a finite set. I can count 1, 2, 3, 4, 5, 6 elements involved there. But if I said, give me the set of whole numbers, or give me the set of numbers that are larger than, let's say, 5. Those are each infinite sets because they go on forever and ever and ever and ever. You can't possibly count them. Okay, so that's an infinite set. All right, so let's wrap up the lesson by talking about subsets. So this is something that you might get tested on. Kind of the other stuff we looked at was just kind of, basic definitions. But these are things that you might have to think about a little bit. So let's take a look at subsets. So if I have set A, which contains the elements 1, 7, and 3, and set B, which contains the elements 1 through 8, then A is known to be a subset of B. And more specifically, A is a proper subset of B because B contains all elements of A and they're not equal to each other. So A is a subset or a proper subset of B. And a lot of times this gets confusing because you have A and you have B, and this kind of looks like a C. So let me make it a little longer. I'll also do it in a different color. Let me do that. So it kind of looks like a C. But that is the symbol for is a proper subset of. Again, if you look at B, it's got 1, it's got 7, and it's got 3. Now, if 2 sets are equal, meaning they have exactly the same elements, they're known as improper subsets of each other. So in this example, we have G, which has 1, 8, and 2, and D, which has 2, 1, and 8. These 2 sets are equal to each other because they have the same elements. 2 and 2, 8 and 8, 1 and 1. So the exact same elements, so they are equal. So we can say they are improper subsets of each other. So we show that by saying G is an improper subset. You see that little bar? Is an improper subset of D. And then also you can say D is an improper subset of G. And let me just label this. This is G is an improper subset of D. All right, so we use the symbol here to denote is not a subset of. So it's just the proper subset symbol with a line drawn through it. So as an example here, we have these 2 sets. We have Q, which has A, M, N, and O. We have L, which has A, D, Z, P, O, and N. So we'd ask the question, is Q a subset of L? Well, no, it isn't. And the reason it's not, this has A and this has A. This has M. This doesn't have M, so no M. This has N, and this has N. And then this has O, and this has O. But because it's missing this M here, it's not a subset. For something to be a subset of another, it's got to contain all of the elements. You can't be missing something. So Q is not a subset of L. Q is not a subset of L. But if I was to change this set, and let's say I was to put an M in there, then it would be a subset, because L would contain all of the elements of Q. So that's what we mean here when we say Q is not a subset of L. So lastly, let's discuss how many subsets can be made from a given set. Well, the answer to that is 2 raised to the nth power, where n is the number of elements that we have. So for example, if I have P is equal to, let's say 5, 7, and 9, well, the number of subsets that can be made from this is 2 raised to the power of 1, 2, 3, or 8. You can prove that to yourself by listing the possible subsets. So one subset would be just the set 5. Then another would be 7. Then another would be 9. Then I would have a subset where I would have 5 and 7. Another would be 5 and 9. And another would be 7 and 9. Then another one would contain all of the elements. And what is the last one? A lot of people don't get this, and it's something you kind of need to be told. Well, the empty set is considered to be a subset of all sets. And why is that the case? That's one thing that many students struggle with. Well, you have to think of subsets as possible choices from the set. So I can choose 5. I have that. I can choose 7. I can choose 9. I can choose 5 and 7. I can choose 5 and 9. I can choose 7 and 9. I can choose 5, 7, and 9, or I can choose nothing. I can choose nothing. So as an example we can kind of understand, let's say that I have a set L. So I have a set L, and L contains 3 elements. It's the elements that are in my lunchbox that I'm bringing to work. So let's say I have chips, I have soda, and I have a sandwich. Make it real simple. So what are the possible subsets that I can make here? We know there's 3 elements, so that we know there's going to be 8 using our formula. But let's go ahead and list them. Again, think about possible choices. What can I take out of the lunchbox? Well, I could take out just chips. I could take out just a soda. I could take out just a sandwich. Now, I could take out 2 items if I wanted to. I could take out chips and soda. I could take out chips and a sandwich. I could take out a soda and a sandwich. And then I could take out all 3 if I wanted to. I could take out the chips, the soda, and the sandwich. And then lastly, I could choose to just take out nothing, right? I could choose to open my lunchbox up and say, you know what, I don't want anything. So my choice is to choose nothing. So that becomes the empty set choice. And so I have my subsets. I have 1, 2, 3, 4, 5, 6, 7, 8. And that is given to me by my formula, which is 2 raised to the number of elements I have. I'm going to have 1, 2, 3 elements. 2 to the 3rd power is 8, and I've listed them there for you. In this lesson, we want to continue to talk about sets. So at some point in your math class, you've probably heard about something known as a Venn diagram. If you haven't, I can promise you by the time you get out of high school, you're going to encounter at some point, either in a math class or outside of a math class. But a Venn diagram is just a way to visually represent the relationship between sets. It's actually a very, very useful thing, even when you're not working with math. So as an example, let's say we have a universal set which contains the elements 1 through 10. Then we have a set A, which contains the elements 1 through 3, and a set B, which contains the elements 3 through 6. So the idea here is that we draw a rectangle to represent the universe or the universal set. So let me just put a U inside of here to say this whole thing represents set U. So all of my elements here should be listed inside the rectangle somewhere. Now I have two subsets of U. I have A, which is a subset of U, and I have B, which is a subset of U. And each of these is represented with a circle. And notice how the circles are inside of the rectangle, right? Inside of our universe. So I can label each circle. I can label one of them as A and the other as B. Doesn't matter which is which. And I would list elements inside of the area that it corresponds to. And one thing I want to bring your attention to right away, I want you to notice how there's a section of overlap. This is used to place any element that is part of set A that is also part of set B. So a common element. And when we start listing things here, we see we have 1, 2, and 3 for set A, and we have 3, 4, 5, and 6 for set B. 3 is common to each, so that's going to go in this section of overlap. Now for set A, I have 1 and 2 that are not common to B, so that's just going to go over here, somewhere outside of the overlap. Same thing goes for set B. I'm going to put 4, 5, and 6 in here, but outside of the overlap. Now, elements that are part of the universal set that are not part of A and not part of B would just go somewhere inside of this rectangle. They just can't go inside of these two circles because, again, they're not part of A or B. So I have 7, I have 8, I have 9, and I have 10 that fit that criteria. So this is our first Venn diagram. Let's just go ahead and label it. This is our Venn diagram. And again, it's a visual way to represent the relationship between the sets. I can look at this right away, and I can tell that I have a universal set that's 1 through 10. I have a set A that's 1, 2, and 3. I have a set B that's 3, 4, 5, and 6. And I can also tell that A and B have a common element of 3. So some key information that I can pull right away just by looking at a picture versus kind of looking at these sets in the roster method and trying to kind of pull information out that way. Now, a couple of things we want to talk about now. The first thing would be the complement of a set. So this is represented, if I wanted the complement of A, I would write A prime or A complement like that with a superscript C on top of the A. So A complement contains all of the elements or members of set U that are not elements or members of set A. So in this case, because set A has 1, 2, and 3, I would just exclude those, and I would say, okay, I have 4, 5, 6, 7, 8, 9, and 10 as the complement of A. And again, I go back to my Venn diagram, I can quickly see that if this is set A, everything inside this circle, and I know I didn't color in the lines perfectly, but just kind of bear with me. Everything outside of that circle is the complement of A. So it's very quickly to get that. I can just see that it's 4, 5, 6, 7, 8, 9, and 10. Very easy to get that information. As another example, let's take B complement. So let's erase this, and let's take, you can put B prime or B complement like this. And in this scenario, I could either do it this way. I can say, okay, this contains 3, 4, 5, and 6. I can mark those out and say it's 1, 2, 7, 8, 9, and 10. Or visually, I could look at my Venn diagram. And if I look at B right here, everything outside of this is going to be the complement of B. So I'm looking at, again, 1, 2, I have 7, 8, 9, and 10. 7, 8, 9, and 10. Now, let's erase this real quick. Let's now talk about the union of two sets. So the union of two sets, let's say A and B, is denoted with a symbol that kind of looks like a U. So we'd say A, let me do it in a different color, union, and then let's return to the other color, B, is equal to, this is going to be the set of all elements of A along with all elements of B. but with one key thing here. We don't want to double list anything, okay? So if I put in all the elements from set A, that's 1, 2, and 3, then all the elements from set B, I've already listed 3. I don't need to list it again. So then just 4, 5, and 6. And again, the way you look at the union is, if I look at my Venn diagram, it's everything that's contained in these two circles. So everything in these two circles. What's not going to go in there would be anything outside of the circle. So things like 8, 7, 9, and 10. Things that are outside of the circles, you can very quickly look at the Venn diagram and get the union. Now, the other thing that we would talk about would be the intersection. So let me erase this real quick. The intersection just looks like a flipped upside down U. So I'm just going to basically reverse that symbol and make it look like this. So this is intersection. And the intersection of A and B is going to be the set of all elements that belong to both A and B. And again, that's where you're going to look at your overlap. So if I look at my Venn diagram, this is the intersection. Again, the set of elements that belong to both A and B. So that's going to have one element. So A intersect B is equal to, we just have one element, and that element is 3. All right, let's take a look at another example. So here we have a universal set where we have the elements A, B, C, D, G, H, N, Q, and T. And everything is in lowercase to keep you from confusing it with the set names. Then we have set A, again, capital A, and this contains the elements G, H, and N. And then set B, which contains the elements T, Q, and N. So the first question I have here is, what is the union between A and B? So A union B equals what? Well, let's fill in our Venn diagram. So let's let this be set A. Let's let this be set B. And in set A, I have G, I have H, and I have N. And notice where I put the N. It's because it's common to A and B. So for set B, I have T, I have Q, and again, I have N. N is in the overlap section because it's a member of set A and also set B. Now, in my universal set, I have elements that are not part of A and B. I know that A falls outside of those two circles. So does B, so does C, so does D. G doesn't, H doesn't, N doesn't, Q doesn't, and T doesn't. So if I want the union of A and B, this is going to be equal to, we'll have G, H, N, T, and then Q. And again, the main thing here is to make sure you don't double list anything. So I have N here and here. It only gets listed once when I fill out this information. What if I asked for the intersection? If I said, and let me kind of go in here and edit. So if I ask for the intersection, the symbol looks like this. Just an upside down U, and I know that's not perfect, but just pretend it is. Again, I'm looking for the overlap between these two sets. So the overlap, if I look at the Venn diagram, it's just going to be right here. That's real easy to get. That's N. So that's A intersect B. And then what if I asked for some other things? Let's say I asked for A complement. A complement. And I could do it this way, or again, I could do it this way. Doesn't matter. Well, that's anything that's outside of A. So I could just highlight this set right here, and I could look for things that are outside of A, and what I'd come up with is T, Q, A, B, C, and then D. And again, it doesn't have to be in alphabetical order. The order is irrelevant when you're listing the elements of a set. And if I ask for B complement, that would be anything that's outside of this circle here. So let me highlight that real quick for you. So for this case, I'm looking at what? I'm looking at A, B, C, G, H, and D. All right, let's take a look at another one. So now we're going to have our universal set, which contains 1, 3, 5, 7, 9, 11, 13, and 15. So basically the odd numbers starting at 1 and going through and including 15. Then set A has 1, 3, and 5. Set B has 3, 5, and 7. and set C has 9, 13, and 15. So let's label this as set U. Let's label this as set A, set B, and set C. So now what you're going to notice is set A and B have two common elements, 3 and 5. So those are going to be put in the overlap section. And then for set A, we have 1 that's outside of that. For set B, we have 7 that's outside of that. And then for set C, we have nothing that's common to A and B. So notice how there's a gap between these circles, right? We don't want any overlap because there's nothing that's going to be common. So for set C, I'm going to write in 9, 13, and 15. Okay, so also in set U, we have 11. That's not listed in any of these sets here. So that's going to go outside of all those circles. So without referencing to this, let's answer these questions here. So we're just going to look at our Venn diagram. So we have A union B. What is that? That's all the elements of A along with all the elements of B. Again, just don't double list anything. So looking at the Venn diagram, that's easy. It's a 1, a 3, a 5, and a 7. Then if I want A union C, what is that? Well, that's 1, 3, 5, and then 9, 13, 15. And then B union C is what? We have 3, 5, 7, and then 9, 13, 15. Let's see if we can do some other things here. Let's erase this. And let's ask for the intersection in each scenario now. So A intersect B is what? Again, that's your overlap here. So that contains the elements 3 and 5. What about A intersect with C? There is no overlap. Those two sets are called disjoint sets. They have no elements in common. And so this right here would be the null or empty set, right? Because this set contains no elements, because there are no elements that are common between set A and set C. Same thing goes for the intersection of B and C. You would put the symbol for the null or empty set. Now we could also go through and we could do the complement of each. So I could do the complement of A, the complement of B, and the complement of C. And again, with our Venn diagram, we can do these very quickly. So for A complements, I would have 7, 9, 13, 11, and 15. For B complements, I would have 1, 11, 9, 13, and 15. And then for C complement, I would have 1, 3, 5, 7, and 11. And again, just looking at the Venn diagram makes things nice and easy to see. If I want A complement, I could shade A and say I want everything outside of that. So that's 7, 11, 9, 13, and 15. If I want B complement, shade B, and I want everything outside of that. So that's 1, 11, 9, 13, and 15. And if I want C complement, I could shade C. And again, I want everything outside of that. So that's 1, 3, 5, 7, and 11. All right, let's take a look at another one. So we have a universal set that contains California, Oregon, Washington, Colorado, North Dakota, New York, Wyoming, Texas, Georgia, South Carolina, Maine, and Wisconsin. Then I have a set A, which is a subset of set U, which contains California, Oregon, Washington, and Colorado. Then I have a set B, which again is a subset of set U, which contains Oregon, North Dakota, New York, and Washington. Now, if I fill this out for set A and set B, what they have in common would be Washington and Oregon. So let's say this is set A and this is set B. So for set A, I would also have California and I would have Colorado. For set B, I would also have North Dakota and I would have New York. And outside of these sets, in set U, let me use a different color, I would have Wyoming, I would have Texas, I would have Georgia, I would have South Carolina, I would have Maine, and I would have Wisconsin. So once we have our Venn diagram built, it's easy to go through and answer some questions. So let's say I start out by asking you for A union B. What's that equal to? Well, that would be California, Colorado, Washington, Oregon, North Dakota, and New York. If I asked you for the intersection of A and B, that would be the overlap section. So that would contain two states, Washington and Oregon. If I asked you for A complement, again, I could highlight this right here. And I could say that A complement contained North Dakota, New York, Wyoming, Texas, Georgia, South Carolina, Maine, and Wisconsin. And then lastly, if I asked for B complement, this would contain the elements. I could erase this, and I could highlight this. Okay, I could highlight this. And I would have California, Colorado, Wyoming, Texas, Georgia, South Carolina, Maine, and Wisconsin. In this lesson, we want to talk about combinations and permutations. All right, so when we get to this section, a lot of students are going to have difficulty determining whether to use our formula for permutations or whether to use our formula for combinations. Basically, we're going to start out with one here where we say that there are 20 applicants for 3 jobs, a JavaScript developer, a data scientist, and a UI engineer. Well, basically the way that you decide here, you're going to be selecting 3 people out of the 20. So if you have the number of ways of selecting R items out of N items, in this case it's 3 out of 20, and repetition is not allowed because the same person can't get the JavaScript developer job, the data scientist job, and the UI engineer job. It's got to be 3 separate people. Well, you want to consider the fact that if the order is important, you want to use a permutation. If the order is not important, okay, you want to use a combination. So here the order is very important to us because it's a different result if I get a job as a JavaScript developer versus if I get a job as a data scientist, okay? So because the order is important, we want to use our formula for permutations, and that's a real easy formula. It's going to be P like this, and then I'm going to put some parentheses. It's going to be N comma R. Okay, the N here is going to be the 20. The R here is going to be the 3. We'll fill that in a minute. This equals, you've got your N factorial over, you've got your N minus R factorial. Okay, so in this case, we're going to have P, and we would say 20 pick 3. Okay, that's how you can read that if you want. And this is going to be equal to 20 factorial over, and I made that a little bit long, so let's fix that. So 20 factorial over, in this case, you'd have 20 minus 3 or 17 factorial, okay? If you want to simplify this, you can. Of course, this key is on your calculator if you're using a TI-83 or 84 or whatever the version is you're using. But let's just go through this one. In the future ones, I'm just going to punch it into the calculator and make it a lot quicker. Let's move this up here. This would be what? It would be 20 times 19 times 18 times 17, so on and so forth. But this part here, because the 17 factorial is going to keep going down to 1, you can get rid of that part and just erase this and say it's 20 times 19 times 18, which is going to be what? Well, 20 times 19 is 380, then times 18 is going to be 6,840. All right, let's look at the next one. So we have the senior class at Denton High School, which contains 60 students, wishes to elect a president, vice president, and secretary. So we're choosing 3 students out of the 60 for these 3 positions. The order is going to matter here, right? If someone gets selected as a president, it's a different result as if they got selected as a secretary. So in other words, let's say that John got picked to be the president, and let's say Larry got picked to be the vice president, for example, and let's say that Steve got picked to be the secretary. Well, if I switch things up, I could have the same 3 students, okay, but they got different positions. That's a completely different result, okay? So in this case, we want to use a permutation. And we remember the formula for that. So I'm just going to type this into my calculator. I'm going to do 60, okay, 60. And then you're going to have that key that says N pick R. So it looks like this, a lowercase n, an uppercase P, and a lowercase r. But I'm going to hit 60, this key right here, and then 3, right? Because there's going to be 3 students selected, president, vice president, and secretary. And if you run that calculation, you're going to get 205,320. So 205,320. And again, if you want to use the proper notation there, you've got this P, and then you've got the first number, that's 60, and then comma 3. Okay, so this is what this is equal to. Again, if you go on your calculator, it's the NPR key. Okay, let's look at another example. So we have the junior class at Bracken High School consists of 250 students. They need to elect 2 representatives for the student council. Okay, well, this is a little bit similar to the last question, but we're going to end up using a different formula here because now the order doesn't matter anymore. Okay, repetition's still not allowed, but the order doesn't matter anymore because let's say John gets the first representative position and Steve gets the second one. Well, it doesn't matter if we reverse that and Steve got chosen first and then John did because they're both going to just be representatives. Okay, so the order doesn't matter here. So we want to use the formula for combinations, and we learned this in the last lesson when we talked about the binomial theorem, right? So we have this formula. It's n choose r. So we have this c and then n comma r here. And this equals your n factorial over your n minus r factorial, and then times your r factorial. Okay, so what ends up happening is we're dividing out the duplicates with this extra part here. Okay, this is all you have to remember because if you've got this part down from the permutations formula, you're just throwing that extra little bit there in the denominator to divide out the duplicates, and that's how you get your combination formula. Okay, so let's erase this real quick. Let's actually plug in the numbers. I'm going to again use my calculator here because you would basically be doing this C here with 250, 2. And I'm not going to set this up. You're just going to hit 250 and then go to NCR. And I'm going to get a result of 31,125. Okay, let's look at another example. So a local high school is having a marathon qualifier. There will be a total of 40 runners that will participate. The first 8 people to finish the race will advance to the state championship. Okay, so do I want a permutation or a combination? Does the order matter here? We know that repetition is not allowed, right? Because if I'm in the first position, I can't also be in the third position. But does the order matter? Well, no, not for our result because it just says the first 8 people. So it doesn't matter if I finished first or 7th, okay? As long as I'm in that top 8, okay, I'm going to advance to the state championship. So we would use a combination here. And again, I would just do C, and then I'm going to put 40, 8. Again, just punch this into your calculator. You're going to do 40, choose 8, and that gives us a pretty big number. It's going to be 76 million, and then you're going to have 904,685. All right, let's just look at one more. So the state championship marathon consists of 40 runners. The top 3 runners will earn gold, silver, and bronze medals. So can we have repetition here? No, right? Because if I finished first, I can't also finish second or third, okay? And then does the order matter? Well, yeah, it definitely matters, right? If I finish in first place, that's a different result than if I finish in second place. In one case, I'm getting gold. In the other case, I'm getting silver. So the order does matter. So I want to use the permutations formula. So I would just use my calculator, or again, you've got this P with this 40, 3, if you want to say it's equal to. You can punch this in on your calculator, or again, you can use your little formula. I just think it's easier to punch it in on a calculator because a lot of these, the numbers are just going to be astronomically big. So if we go ahead and punch up 40, and then you do your NPR key, and then 3, you're going to get 59,280 as a result. In this lesson, we want to look at some probability word problems. So at some point in your algebra course or your pre-calculus course, you're going to come across a small section on probability. And I just want to go through some basic word problems that you're going to see and talk about how we can solve these guys. So I'm just going to jump right in. I'll just kind of explain things as we go. It's a very, very easy topic overall. So Jason flips a coin and then rolls a 6-sided die. What is the probability that the coin lands heads up and, okay, I'm going to highlight that, and the die shows an even number. Okay, so when you deal with these problems, you're going to have problems that say and. So some event occurs and some other event occurs. In this case, one event is flipping a coin and him getting a heads up, and the other event is rolling a die and getting an even number. So a 2, a 4, or a 6. Okay, when you hear the word and, you need to be thinking about multiplication. So I would take and use this formula. The probability of some event A and some event B happening, okay, in this case, we'd say the coin landing heads up and also the die showing an even number, is equal to the probability of this event A happening times the probability of this event B happening, okay? Now, this is given the fact that they are independent events, meaning the first event does not impact the result of the second event in any way, shape, or form, okay? If he flips a coin, that does not impact the result of rolling a 6-sided die. Okay, so these are independent events. We can just use this formula as it's given. So what we want to do here is just think about the fact that the probability for flipping a coin and getting a heads up is going to be what? It's going to be a half or 50%. We all know this because we've thought about that throughout life at some point, flipping a coin saying, hey, my odds are 50-50. Well, how do we show this mathematically? Where does that 50-50 or the 50% come from? Well, essentially what you do is you think about the number of different ways that you can get an outcome from flipping a coin. Well, you can basically get a heads up or a tails up, right? So there's two possibilities. So I'll put that in the denominator. And then think about what you're looking for. What's the result? Well, I want a heads up, and that can only happen one way, right? So I would put that number in the numerator. Okay, and as we do more of these, this will make more sense. But essentially, this is the formula you want to use. That's where 1/2 comes from. This is basically the number of favorable outcomes. In this case, a favorable outcome would be landing heads up over the total number of possible outcomes. And the possible outcomes here would be landing heads up or landing tails up. Okay, so I know that's 1/2. So let's just say that this satisfies the probability of event A. Now, what about the probability of event B? Let's say that's the die showing an even number. Well, with a die, if it's 6-sided, it can land on a 1. Let me just kind of write this down here in a different color. A 1, a 2, a 3, a 4, a 5, or 6. So we know that the 2 is an even number, the 4, and the 6. Okay, so 2, 4, and 6, those are even numbers. So how many different favorable outcomes can I have? Well, I have 1, 2, 3 favorable outcomes that are possible out of a total of 6. So I would put 3 over 6, which you can simplify to 1/2, okay? And then you just multiply the two together, and let me just kind of erase this. You multiply the two together, and you get 1/4, okay? Now you can leave it as a fraction and say it's 1/4 of the probability, or you can convert it to a decimal, which is 0.25, and then to a percentage and say it's 25%, okay? So essentially the probability of this Jason guy flipping a coin and getting a heads up, and also taking a die and rolling it and getting an even number is 25%. Okay, let's look at a slightly more challenging problem. And in this case, we're going to have dependent events. So Allison, a teacher at a middle school, has 5 boys and 6 girls in her class. Allison randomly selects 3 different students to walk up and give a presentation. Once the presentation is over, the student will leave for the day. What is the probability that the first student is a boy, the second student is a girl, and the third student is also a girl? So you see the problem here is that these events are not independent, okay? Once she picks a student, and we're looking for her to pick a boy first, okay? Then the next time we want her to pick a girl, and then the next time we want her to pick a girl, but each time she's picking, the class size is changing, right? So the number of boys is changing, the number of girls is changing, whatever it is in that scenario, but the class size is constantly changing, so we have to readjust our probability, okay? So we're still going to think about multiplying the probabilities together, but you use a different formula for this. If it was just 2 things, here it's 3, but let's say it was 2 things. So the probability of A and B, okay, if these guys are dependent, and it's just 2, it would be the probability of A times the probability of B given that A has happened, okay? So given that A has happened, what's the probability of B happening? Okay, and in this case, we're going to adjust it because we have one more thing to consider, because now we're thinking about the probability that the first student is a boy, Okay, so that happens. Then the probability that the next student is a girl, okay? And then the probability that the third student is also a girl. So again, you have and, so you're thinking about multiplication, okay? So what is the probability on the first graph that that student is a boy? Well, there's going to be 5 boys, okay? So there's 5 possible choices in there that's going to be boys out of a total of 5 plus 6 is 11 total students. So the first number we're looking at is, I'm just going to write this down here, 5 over 11. I'm just going to put this as the first, okay? So the second is going to be what? Well, if I go back up, I know that the student leaves. He can't be rechosen now. And there's going to now be what? Well, there's 1 less boy, so there's 4 boys. And there's the same number of girls, but the total number in the class now is 4 plus 6 or 10. Okay, so if I think about picking a girl now, it's going to be 6 girls out of a 10 student classroom. Okay, let me just erase this. So let's go down here and put that. Now it's 6 over 10. Okay, so this is second, you'd say. And now what's going to happen for the third choice when we go back up? Well, now there's, let me just kind of scratch this out again, say this is 4. This is going to go down to 5. There's a total of 9 students, and there's 5 girls. So there's 5 over 9. Okay, let me just erase this again. And now I'll say this is 5 over 9. And this is going to be the third pick, okay? So the probability of picking a boy on the first run is 5 over 11. Then given the fact that that event has already happened, now there's a 6 over 10 probability of picking a girl. Now, given the fact that both of those events happened, the probability on the third pick that it's a girl is 5 over 9. Okay, so again, to get the final probability or the probability that all these events happen, so this and, she picks the first student as a boy, and she picks the second student as a girl, and she picks the third student as a girl, it's going to be the product of these probabilities. So before we multiply, notice you can cancel this with this and get a 2 here. And then 6 divided by 2 would be 3. And then 9 divided by 3 would be 3. Okay, so I'm going to put a 1 here. And basically what you'd have is 5 times 1, or 5, over 11 times 3, which is 33. So you have 5 over 33, which is the probability of picking a boy, then a girl, then a girl. All right, so now let's talk about some word problems that involve this or. So when event A happens or an event B happens. So with this, we're going to be adding now. So when you hear and, you got to be thinking about multiplication. When you hear or, you've got to be thinking about adding. Okay, but there's a trick to this. And let me just kind of go through this with this problem. So Katie has 6 nickels and 7 dimes in her pocket. 5 of the nickels and 1 of the dimes are Canadian. The others are from the US. Suppose Katie randomly selects a coin from her pocket. What is the probability that it is a dime or is from the US? This is the key word here, the or, okay? So what you want to be thinking about is the probability of some event A happening or some event B happening is the probability of the event A happening plus the probability of the event B happening minus, okay, this is important, minus the probability of A and B happening, okay? And I know a lot of people use set notation there, so you might see this as well, okay? So the intersection of A and B. However you want to write it, it doesn't really matter. I'm just going to stick to writing and. I think that's a little bit easier for us to understand. Okay. In this particular case, we don't have something known as mutually exclusive events. Mutually exclusive events are 2 events that can never occur simultaneously. So in this particular case, we don't have that because it says, what is the probability that it is a dime or is from the US? Well, we have dimes that are also from the US, so we have to use this full formula. Okay, if we didn't have dimes from the US, we could knock this part out. Okay, this is going to take out the double counting. So let's go through real quick and think about what's the probability that it's a dime. Well, we know that she has 6 nickels and 7 dimes. Okay, well, 6 plus 7 is 13. So 13 coins overall, 7 of them are dimes. So the probability of having a dime is 7 over 13. Then plus, what's the probability, okay, that the coin is from the US, meaning it's not Canadian? Well, it tells you that 5 of the nickels and 1 of the dimes are Canadian. So 6 out of the 13 coins are Canadian. So 7 out of the 13 are American or US currency. So 7 over 13. 7 plus 7 is 14. 14 over 13 is a number larger than 1. When we deal with probabilities, it's either 0, okay, meaning it's not going to happen, up to and including 1. 1 means it's certain to happen. Anything in between means it may or may not happen, okay? But you can't get a probability less than 0 or greater than 1. That doesn't make any sense, okay? So that would be a red flag if you forgot to subtract this out. So all we need to do to fix this is subtract out the probability of A and B occurring, okay? So how many dimes do we have that are also from the US? Well, let's think about that. We know that there are 7 dimes in her pocket, okay, total of 7. And it says that 5 of the nickels and 1 of the dimes are Canadian. So that means that 6 of the dimes are from the US, okay? So that tells me that I need to subtract away 6 over 13, right? Because 6 of the dimes are from the US. So if I crank this out now, I get 7 plus 7, which is 14, and then 14 minus 6, which is 8. So I get a result of 8 over 13. So that's going to be the probability that she picks a coin that's going to be a dime, or it's from the US. Okay, let's look at another example of this. And now we're going to see mutually exclusive events. So Beth has a fruit basket which contains 4 apples, 4 peaches, and 5 pears. If she randomly selects a piece of fruit, what is the probability that it is an apple or a peach? Again, when you see this keyword or, you're thinking about addition, okay? But in this particular case, you don't need that full formula, okay? Because it's not possible for her to select something that's an apple and a peach at the same time. So again, when you think about the probability of some event A happening or some event B happening, it's the probability of A plus the probability of B, and then minus the probability of A and B occurring. And I didn't write my A there. So A and B. Well, in this particular case, you can get rid of this because it's going to be 0. Again, you cannot have a piece of fruit that's an apple and a peach at the same time. Maybe they're working on that. I'm not sure. But in this scenario, it's not possible. So we just think about the probability of A. Let's say that's where she selects an apple. Well, there's 4 apples out of a total of 4 plus 4 plus 5. 4 plus 4 is 8. 8 plus 5 is 13. So the total of 4 over 13, okay, that's going to be your probability of picking an apple. Then plus, what's the probability of picking a peach? Well, again, it's 4 over 13. So all I have to do is just sum these, and I get 8 over 13. All right, so let's wrap up the lesson by looking at an example where we use our binomial probability formula. So the desks in a classroom are organized into 4 rows and 4 columns. Each day, the teacher randomly assigns you to a desk. You may be assigned to the same desk more than once. Over the course of 5 days, what is the probability that you are assigned to a desk in the front row exactly 3 times? Okay, so if you are dealing with a scenario such as this, where you have repeated independent trials, okay, so this is independent because every day you're randomly assigned to a desk and you can sit where you've sat before. And the outcome in each trial is either a success, meaning in this case you will get assigned to the front row, or a failure, okay? So if you want to find the probability of R successes in N trials, you can use this formula. So let me write this down here, and we'll come back up in a minute. So N choose R, okay, we'll remember that. And then times P raised to the power of R. P is the probability of a success. So on a single day, what's the probability of you getting seated in the front row? I'll get to that in a second. Then times 1 minus this P raised to the power of N minus R. So N is the number of trials. So if we go back up, we know that this is going to happen for 5 days. So over the course of 5 days, so N is 5. And the number of successes we're looking for is R, right? So 3 times is we're looking for that number to happen. So N is 5. N is 5. And R is 3. Okay, so you're just plugging things in. So you have 5 and 3, okay? Then P is the probability of a success on any given day. Well, if we go back, we know that there's a total of 16 desks, right? 4 rows and 4 columns. 4 times 4 is 16. So in the front row, you're going to have 4 desks. So that means you have a 4 over 16 or 1/4 or 25% probability of getting seated in the front row on any given day. So we're going to put a 1/4 here. You could use a decimal if you want. It doesn't matter. It's going to be the same result in the end. R again is 3. And then 1 minus 1/4. If you're using a fraction, you would do 4/4 minus 1/4, which is 3/4. And then raised to the power of n, which is 5, minus r, which is 3. So this is going to be squared. Okay, so once you have this set up, you can just erase this and crank this out. So on a calculator, 5 choose 3 is going to be 10. Then if we think about 1/4 cubed, that's going to be 1 over 4 cubed is 64. Then if we think about 3/4 squared, 3 squared is 9, 4 squared is 16. Can I cancel anything before I multiply? I can just get rid of this. I don't need it anymore. Can I cancel anything? Well, yeah, I can cancel a factor of 2 here and here. So this would be 32, and this would be 5. So 5 times 9 is 45 over, what is 32 times 16? That's going to be 512. So 45 over 512, that's going to be your probability of getting seated in the front row exactly 3 days out of a total of 5 days.